Starting our last section, the exams, by the way, aren't graded, and I just looked at my schedule, and I have no free time until 4:30 today, so I probably won't get them graded today. I, believe it or not, have class or meeting the entire time from now on. But I will get them graded soon. We're going to start in with astronomy. By the way, I noticed everybody finished the exam pretty quickly, so I hope that means you did really well, right? I want you guys to score well. That's a good thing. So let's get started with astronomy. So the solar system. The solar system is the system of things that orbit Sol, Sol being our sun. So it consists of its primary object, the sun, the vast preponderance of mass in the solar system. Now, we've moved on a lot since physics, but we've used the word mass from time to time. So just as a reminder, can you tell me what mass is? Looks like... Go ahead, Ivy, or Leslie.
I think it's like the measure of like, kind of like the quantity of what something is, and it has nothing to do with like the gravity part.
Okay, she hit the two things that I was really concerned about. It's how much matter is present, and it's what gravity depends on. When we talk about astronomy, gravity becomes super, super important for us to remember. Gravity is a force that is a central force. It's pulling everything in toward the object. So if we were to take Leslie as an example, Leslie is applying a force to each and every one of us that's pulling us directly toward Leslie. And that force is proportional to the product of her mass and my mass, the force on me, her mass and Ivy's mass, the force on Ivy, and so on. It's also inversely proportional to the separation. So if I cut the distance between Leslie and me in half, it doubles, not doubles, it quadruples the force because it's inversely proportional to the square of the separation. So if you cut the distance in half, then you divide by 1/2 squared, you have 4 times the force. So when things get closer, the force gets bigger. Now the force of gravity is typically small between everyday objects. I talked about our gravitational attraction to Leslie, but none of us feel that attraction. It's there, but it's really small. We do feel the gravitational attraction to the Earth. What's the difference? The Earth has a very, very large mass. Now, we're a large distance from the center of the Earth as well, and that makes it much smaller. But because of the Earth's really big mass, like on the order of 10 to the 24th kilograms, then that force is just huge between us and the Earth, what pulls us down. Gravity is the dominant force that describes why these things are doing what they do, orbiting the sun or part of the sun. The sun is held together by gravity. The force of gravity, the mass of the sun pulling on each of the atoms is what holds them in there. And are crushing them in, making so it's very high temperature and pressure at the core, which in turn makes the core erupt in nuclear explosion. We have planets and moons orbiting the sun. What's a planet? Originally, now don't everybody write this down for your potential test question, or you get a lower score for originality. Originally, planet was a wandering object. Planet is the Greek word for wanderer. And so the planets were things that the Greeks looked up to the sky and they saw that every night all of the stars appeared in the same position relative to each other, but they were rotating. But there were some that moved with respect to all the other stars, so they called those planets. So the definition of planet was just based on the things I see that are not moving with the stars. We now have a much more complicated definition of planet, but that's the original definition. So planets are objects that are going as we understand today, going around the sun that are close and orbiting it. Moons are things that are orbiting another object besides the sun. So the Earth has one moon, or you might have read the Earth has picked up a second quasi-moon. Have you guys read that? There is a second object that is an asteroid that has come close to Earth and is going close enough to our speed that it's going to be orbiting with the Earth for, I think it's a few hundred years or something like that. I don't remember the time frame. So it will appear to us as a moon for a fairly long period of time before it leaves us again. So right now, one can say we have two moons. One that's the size of a refrigerator and one that's huge. I don't actually remember the size of the satellite, but it's small. So moons are things that orbit other objects. Now notice I didn't say that orbit planets, because asteroids are little chunks of rock out there. There are a lot of asteroids in orbit between Mars and Jupiter, but there are other asteroids besides just those, little chunks of rock, that are orbiting around the sun, but some of those asteroids have a moon orbiting around them. So Ida and Dactyl is two asteroids that are orbiting around each other as they orbit around the sun. Pretty complicated stuff out there. We'll also learn that stars, our sun is not the only star, it's just the nearest star. A lot of stars are in binary systems, which means you have two stars that are orbiting each other. And there's actually at least one easy to point out example. If you know the Big Dipper, you have the second star in the handle. Right above it, there's a faint one. And if you look at that faint one with the telescope, you can see two stars. And if you look at those with the spectrometer, you can see that each of those two stars is actually two stars. So what looks like one star to our naked eye is actually four stars, and these two are going like this around each other, and these two are going like this around each other. And then they're going like that. So it's a double-double. It's double star, they're orbiting. It's very complicated. And then comets. What did I say asteroids were? I know what I said, by the way. I'm asking to make sure you do. I said they're rocks. Comets are snowballs. Now, snowballs isn't purely accurate. It's ices, not just water ice, but other things that are volatile ices, and rock. So it's a mixture of ice and rock. We call them snowballs because they've got a lot of ice, but they do have some rock in there. It's like a good old snowball fight that you have. I don't know, we don't have any snowball fight traditions here, right? When I was in graduate school, there was a tradition of the first snowfall, so there's hardly any snow. All of the fraternities would come and start a snowball fight with the dormies. And there's a lot more students in the dorm than there are in fraternities. And so sheer numbers means that the dorm students would always overpower them and drive them back to the fraternities, and things would get really nasty, and people would be basically throwing rocks at each other and using baseball bats, and people had to go to the hospital because of the annual snowball fight. That's what I think of for a comet, is the, quote, snowballs they were throwing at each other. The tradition stopped while I was there. You know why? We went 1 year without snow. That's all it takes to stop a tradition. Okay, so let's move on. Here's a picture showing, not as an accurate representation, but the planets that are in our solar system. So we have the sun. The sun is absolutely huge compared to everything else. So there's a portion of the sun. And then we have the inner planets. Now, this is not showing all the moons, but it shows one. So we have, can you name these planets in order? Okay, the first one here is Mercury. Mercury, followed by Venus, followed by the third rock from the sun. Hence the TV show of the name, Third Rock from the Sun, Earth. What's the last one here? Those are combined, called the terrestrial planets or the rocky planets because they're rocks. Right? If you look at the Earth, it's a big chunk. Now, this shows a moon, the moon of the Earth. So there's Luna. It's not the only one of the terrestrial planets that has moons. Mars has 2 moons. Those moons are Phobos and Deimos, or Fear and Terror. They're, I think, supposed to be twins in mythology. Why do we not see the 2 moons there? Because they're small. Most likely, they're captured asteroids. Asteroids that came close and the gravity of Mars locked them in so they couldn't get away. So Mars has 2 moons. Now we go beyond Mars, and we have the next 4 planets. Jupiter, what are the next 2? And finally, now you'll find I pronounce it Uranus. It's an alternate pronunciation. I do that so it takes away many of the jokes. But somebody pointed out you can make jokes with the pronunciation Uranus too. But it takes away the obvious jokes at the very least. These here are all much bigger than the terrestrial planets. These ones are called the Jovian planets, named after Jupiter, or the gassy planets. You can actually subdivide them. The first 2, Jupiter and Saturn, are called the gas giants, and Neptune and Uranus are the ice giants. There are some differences in them. You can tell differences in them. Which ones of these do you guess would have moons? Okay, we had one person said Jupiter. Yeah, that's a perfect color. Okay, so Jupiter has 4 moons that we call the Galilean moons that are big, and it has somewhere above 50 smaller moons that are probably captured asteroids. Has a lot of moons. They find lots of moons there. I said somewhere above 50. Last time I saw it was in the 60s, but it could be in the 70s or 80s for all I know, because they're constantly looking and finding other objects. Okay, what about Saturn? Well, the rings, you could actually think of them as moons if you wanted to, because the rings are made up of ice chunks, some the size of houses, some the size of little tiny flakes, not a snowflake, but like grain of sand. The gaps, like you see the gap here, those are caused either by moons or by resonance patterns. But Saturn has lots of moons as well. It has one major moon, Titan. So it has one major moon, which is probably further out than that, and other smaller moons. What about Neptune and Uranus? They also have lots of moons. Neptune has Triton. Titan and Triton, it's kind of, they sound a lot alike, but remember, Neptune is the sea god, and he holds a Triton, hence that's how to keep that one straight. And Uranus, well, it has moons as well. What's not shown in this picture that everybody wants to be shown? Pluto. So let's consider Pluto. Is Pluto a rock? Answer: no. Is Pluto a gassy planet? Answer: no. It's not like either of the two categories. It's different. And it was considered a planet because, well, when they were in that Uranus, Neptune, we have them in the wrong order. I was just listening along and didn't pay attention. My very earnest mother just served us nachos is what we use now. I'm sorry, I wasn't paying attention. We've got those in the wrong order. It's important. It's important for this story. In the early days of planets, first of all, we have, what did the Greeks see? The Greeks saw wandering objects, and of those wandering objects, they saw Mercury, Venus, Jupiter, Saturn. And, the sun they probably considered a wandering object. The moon they probably considered a wandering object. The discovery of Uranus, it was actually discovered before William Herschel, but the person who discovered it didn't know what he was seeing. William Herschel is the one that gets credit for it. He and his sister Caroline discovered Uranus. I think his sister was working with him at the time. And he actually wanted to call it King George's star. Or I think it was like George's Sidereus was the name he proposed. But that was rejected because all of the planets have to be named after gods. It's a rule. And so it's named after Uranus, which is a god. And in examining the orbit of Uranus, the orbit is demanded by gravity. And when they looked at the orbit, they said, wow, the orbit is not the shape it should be. It's got some wiggles. What would cause those wiggles? Other massive objects that are passing around. And so they said there must be another massive object that's out beyond Uranus that's causing the wiggles. We've gone past the wanderer definition now because they can only see this with the telescope. But they predicted, based on the wiggles, there should be a massive object here. And so they turned their telescopes there and boom, they saw an object, Neptune. And so they measured Neptune's orbit and everything, and they're all, yay, this is a great, great day for physics, for science. Because the scientific method, we saw something strange, the wiggles in the orbit. We made a hypothesis that those wiggles were caused by some massive object. And then that made predictions of where it should be and what its mass should be. And we looked, and lo and behold, we found an object in the right position with the right orbit and the right mass. Right? That's the way you like the scientific method to work. Well, then as they examined Neptune, the first predicted planet, Neptune's orbit didn't quite match either what they expected. And so they said, well, there must be yet another massive object out beyond Neptune that's causing the wiggles in Neptune's orbit. And so they predicted where it should be, and they looked, and lo and behold, they found Pluto. And they said, hooray! We found it again. Isn't life grand? Duh. A little further analysis showed Pluto wasn't the right thing. It didn't have nearly enough mass. It just happened to be where they predicted. And so had to scratch that one off. Pluto is not a success. But they'd already named Pluto a planet. Hooray! And so it remained listed as a planet. Even though it didn't match what they were looking for, it didn't have nearly enough mass, or the right one. And so they continued to look until finally, with the advent of relativity and the understanding of a massive object, such as the sun, warps the space-time continuum, the actual orbit is now explained with relativity without the necessity of another planet out there. And so we don't believe that there is another planet out there. But then Pluto, what of Pluto? Pluto was called a planet. It didn't have the right properties. The biggest thing that is not planet-like about Pluto is its mass. Pluto's smaller than some of our moons. And so scientists decided we've got to strip Pluto of planethood. Okay, that was decided. We've got to do that. How do we do it? And there was a big convention, and not everyone, of course, agreed that it had to be stripped, but the majority did. And so they came up with a definition for a planet, which we won't go through that definition right here, but they came up with a definition that's mathematical that says it has to have a big enough mass for gravity to form it into a sphere. Pluto does. And it has to have a big enough mass that it dominates its orbit, that it clears up everything else in its orbit. Pluto does not. In fact, Pluto has a moon that's like 1/4 of its mass. Charon is like 1/4 of the mass of Pluto. And so some people were saying we should probably call this a double planet, 2 planets orbiting each other. But what we have now is Pluto is called some will call it a minor planet. It's not fitting the planet model, but it's a special object. There are other objects in that category. There's Ceres, which is an asteroid. There's, Quawa? Wow. I can't remember the names. Ham is something or other. Haumaka. I can't remember the name suddenly. And Eris. Eris is larger than Pluto. Eris is an icy object like Pluto that's larger. So Pluto is not even the largest of its kind. Pluto is like a comet. It's like half rock, half ice. And so there's another thing that's significantly different about Pluto compared to the other planets. How did we get our solar system? This is something that obviously can cause argumentation in a school like Union College, where we definitely believe in creation. And, the Bible says in the beginning, God created the heavens and the earth. And so the standard answer is God created our solar system. Well, science, of course, these days starts with the assumption that there can be no divine interference. And so science won't allow for that answer. And so science has come up with its answer, and some Christians, and I'm one of them, accept the scientific answer as the way God created the solar system. Others say, no, he created it just like it is today. So here is the scientific theory for how the solar system came to exist. It's called the solar nebula theory, as you see up here. Nebula means a cloud. So the solar nebula is a cloud of gas that ended up becoming our sun. Now you have this cloud of gas. It's a lot of mass, but it's really spread out. And remember, gravity was inversely proportional to the separation squared. So if things are farther apart, gravitational force is weaker. And so if you have a really, really thin cloud, gravity is not strong enough to overcome just the average kinetic energy that stays a cloud. And so the theory is that we started that way, a cloud of dust and gas. And then something happened. A shock wave passed through the cloud. A sonic boom is an example of a shock wave. A shock wave brings a high pressure and makes things get closer together. But what happens to gravitational force when things get closer together? It goes up. And so the gravitational force gets bigger because of the shock wave bringing them closer together. And as a result, gravity is strong enough to make things start clumping. And once things start clumping, gravitational force gets much stronger because you have much more mass at the center. And it all starts clumping. But this gas cloud had motion, right? Molecules are moving around. So on average, there's going to be just a little bit of average rotation. And as things get pulled in, it's just like an ice skater. What happens to an ice skater's rotation rate when they pull their arms in? They spin faster. And so the same would happen with the solar nebula. As gravity pulls it in, its rotation will spin faster. And so the theory is that initially we had this clump form because of the shock wave, but because of the rotation, it started flattening out, and we end up with a shape something like this. So pretty much everything is in one plane. We have the Earth You got to keep going way out here. I'm going to fudge on distances. So you have the planets out here all in that plane. And I say they're all in that plane. All of them are very close to in the same plane except for one of them. Do you know which one is not in the same plane? I'll give you a very obvious hint. It's the one that's the hardest to notice if it's not in the same plane. Not Neptune, the other end. Mercury. Mercury is not quite in the same plane. You can see in my dot picture, Mercury is a little bit farther off the line than the rest. But because it's so close to the sun, you don't notice its tilt nearly as much as you would if it was farther out. So Mercury's the only one that's not really close to that. And it makes sense because if you look at the picture there, you have more dispersion in the vertical plane as you get closer to the center. And Mercury's in that region close to the center, it's more dispersed. So they're all pretty much in that plane, orbiting all in the same direction. Now there's another object here that I didn't show. Which planet? Did I not show? I didn't show Pluto, a minor planet or a dwarf planet is the technical name. Well, Pluto is also a bit off of this plane. And it turns out that Pluto isn't alone. There are a lot of objects out there. We call them Kuiper Belt objects. And then beyond that, the Oort cloud. So there's more things there, but that's what we believe. That's how we believe we got here. So how do the planets form then? How do we get these planets if everything's being pulled in by gravity? Think about it. Give me some ideas.
How do we get planets? What was the question?
How do we get planets instead of everything being in the sun?
I mean, one theory that I heard, what everyone has heard, is they said that our system started by the Big Bang Theory, but I don't know how that all relates to.
Not our solar system. The universe is what the Big Bang Theory is about. But our solar system is only about a third of the age of the universe, according to the best scientific knowledge. Our solar system is a little under 5 billion years old, whereas the universe is around 13.8 billion years old. So it's not the Big Bang for our solar system, according to science. But the answer for how the planets formed is when you had that shock wave, you had different centers that started clumping. And one of those got the lion's share and became the sun. But the other centers that started clumping would start forming their own objects. And if those objects are big enough, they're going to be, following their path around the circle and not fall into the sun because of their orbit. And so it's believed that's how we formed. We formed while the sun was forming. We were just a clump, but we weren't the lucky ones with enough mass to be the dominant one. We were reasonably close to the sun. Because we're reasonably close to the sun, during the formation time, it was really hot in our neighborhood, which meant that only molecules with a high melting temperature could stick together. And so the Earth is dominated by, how many elements dominate the Earth? I think this was on your test. 8. And what's special about those 8 elements? They're things with generally high melting temperatures. So that's why we have the high melting temperature stuff. That's why we're relatively small compared to Jupiter, Saturn, Uranus, and Neptune. Jupiter, Saturn, Uranus, and Neptune formed beyond what's called the ice line. Out there during the formation of the solar system, it was cool enough that you could have condensation of volatiles. Condensation of things like water and hydrogen and helium. And so since those things could condense, those could join up the forming planets. Now, once the planet gets big enough, it can hold on to those. Earth never got big enough to hold on to hydrogen or helium. We simply don't. Now, you might ask, how do we have hydrogen and helium if we can't hold on to hydrogen and helium? Does that seem like a logical question? No? Well, to me, it seems like a real poser of a question. How do we? Well, the answer is hydrogen and helium are products of radioactivity. And so those are constantly being produced on Earth as you have things like uranium undergoing its decay. It creates, I think, 8 helium as uranium decays into lead. And so that's constantly producing helium. And when the helium is released into the atmosphere, we lose it. Hydrogen is also being produced by other radioactive decays that we didn't talk about. So that's how we still have these things, because they're constantly being produced. So if it wasn't for radioactivity, we wouldn't have hydrogen. You know what? We talked about hydrocarbons as being really important, like our bodies are made of hydrocarbons. If we didn't have hydrogen, we'd kind of be in trouble. So it's good that we have a replenishing, so any hydrogen that goes into gas and gets lost can be replenished. All right. There are some words here. I haven't been focusing on my slides. I've just been telling the story. So here's some words. Proto-sun. I missed. Proto-sun. You know what a prototype is. Well, proto-sun is the prototype for the sun. It's the forming sun. It's going to become the sun if it ever goes into production, which, of course, it did. So you have the proto-sun, but then you also have, away from the center, planetesimals. Planetesimals are little forming protoplanets. We have 2 different terms, protoplanet and planetesimal, and it depends on the size. So the planetesimals are other little centers where material is clumping. Now, a question about this solar system model, and no, I never want to install software in the middle of class. I think Microsoft would learn that. Which of the following orbits around the sun? So which of these things orbit around the sun? Everyone's here. Choose you this day. All right. $2,006. It's a pretty clear lead there, but well, yeah, I'm not going to ask the student because it's pretty clear. All of the above was the correct answer. Planets, objects like the Earth, clearly orbiting around the sun. It used to be, if you were born, 1,000 years ago, you would have said, heresy! Burn him! Burn him! If I were to tell you this, that the planets are orbiting around the sun. Because what did they believe 1,000 years ago? That the Earth was the center and everything was going around the Earth, that the sun was going around the Earth. There are still flat earthers who have some weird beliefs with the sun neither going around the Earth nor the Earth going around the sun doing some kind of pattern like this up there in the sky. But there have been lots and lots of experiments. Experiments actually before the birth of Christ, showing that the Earth was a sphere and the sun went around the Earth. There was experimental evidence before the birth of Christ that the sun is going around the Earth. But still, up until around 500 years ago, it was accepted that the sun was going around the Earth. But now everybody accepts it's the only easy explanation for everything, that the planets are going around the sun. Comets, I only talked about them as ice balls, but those comets are things that are out there in orbit, some of them in orbits in the region of Pluto, some further out. And if their orbit gets messed up, so they come hurtling in toward the sun, then they become a comet. So they're ice balls out there until their orbit gets messed up and they come flying in toward the sun, then they're a comet. And when we see the comets, we're seeing them because they're getting close enough to the sun that the sun's radiation is causing them to melt, leaving a cloud behind them. I say cloud behind them. It's actually a cloud that points away from the sun because the sun is pushing that material away. And then it's lit up by the sunlight. Asteroids are rocks that are out there orbiting. And like I said, there's a lot of rocks between Mars and Jupiter. We call it the asteroid belt. But there are other asteroids besides those, such as the one that the Earth has picked up as a kind of pseudo-moon right now. The sun, I've said, is a star. It's our closest star. The sun is something like 8 light minutes away. That means it takes 8 minutes for light to get from the sun to us. If the sun suddenly stopped producing light, we would still see light from the sun for 8 minutes because it takes that long for the light to get here. So it's composed mostly of hydrogen. And when we say hydrogen, you know what we mean? We mean naked protons. It says hydrogen in the plasma phase. Plasma is a term that means ionized gas. Well, if you take a hydrogen atom, that's a proton with an electron going around it, and you take away the electron, what are you left with? A proton. So hydrogen in the plasma phase means protons. But you also have the electrons, but just not bound to the protons. So you have a bunch of protons, you have a bunch of electrons. That's what primarily makes up the sun. In the core of the sun, that's in the very heart of the sun, the center, you have such high temperature and pressure that these protons flying around slam into each other so hard that they get close enough to overcome the repulsion. You know, protons are positive. Two positive charges, they approach each other, there's going to be a force that repels them, pushes them apart. And so usually they come toward each other and they repel and they fly away. But if they're going really fast, which means they have a very high temperature, they can actually come and hit each other. And when they hit each other, there's a very short-range force, the strong nuclear forces actually, too, that will hold it together. And it's in a lower energy state, so it sticks together. And because it fell to a lower energy state, it gives off energy equal to the difference. So you have them coming really fast, hit each other, stick together, and give off energy. That's the fusion process. That's what's going on in the core of the sun. So it's called their thermonuclear fusion. Hence, if you own Oakley sunglasses, somewhere on the box it probably says thermonuclear protection. That's their little joke. It's protecting you from the radiation coming from a thermonuclear explosion, i.e. the sun. So that thermonuclear protection slogan is saying it's protecting you from sunlight. About 4.5 million tons of mass are converted into energy every second. 4.5 million tons. That's a huge amount of mass. Every second that's converted into energy. So the sun is losing mass. It's losing weight, if you will, because on Earth that would translate into weight, at a very rapid rate. But it has so much mass that that's an insignificant change. Based on this rate of burn and what we understand of the sun is about 5 billion years old and has enough fuel for 5 billion more. So the sun should have been burning, according to scientists, for about 5 billion years, and it'll continue to operate for about 5 billion more years. In 5 billion years, you and I will be in heaven. Mm-hmm. But at that time, the sun, if God does not do something to change it, the sun will become a red giant. It will really expand. it'll be cooler because red is a colder color than the white that the sun is now. So it will cool down and expand, the two go hand in hand, such that the photosphere of the sun, what we see at the surface of the sun, will be beyond Earth's orbit. The Earth will be inside the sun. Obviously, this will incinerate the Earth. So the Earth will be destroyed in about 5 billion years by the sun. Now, that's not what the Bible's talking about with destruction, right? Armageddon. Just making sure we're clear on that. But that's what will happen if there is nothing to intercede in the intervening time. Just a small fraction of the sun's energy reaches the Earth. That's just a geometry game. I'm giving off sound. The sound that I'm giving off is going in all directions in this room. Each one of you is only getting a small fraction of the total energy of sound that I'm giving off. Now, if you were farther away, like if you were in a car parked across the parking lot and there were no windows in the way, you would still get a little bit of sound, but it would be a much smaller fraction because of the geometry. Farther away, much smaller angle that you're going to receive. Well, now just consider the distance we are from the sun. It's a minuscule fraction of the sun's energy that we're receiving. Okay, our next question. Strictly speaking, in every second that passes, the mass of the sun does what? Yeah, I did answer that. All right, we've all answered. Rachel Hammond. What you think?
I put C when it induces, just because you said that it would eventually expand into the red giant, but I wasn't sure. So.
Okay, now she is correct that I said that the sun will eventually expand to become a red giant. But that's not an increase in mass, that's an increase in size. The two aren't the same. The correct answer here was actually the second most common answer. Decreases. Remember, it was 4.5 million, was it tons per second that it's losing? I'll go back here just to make sure. 4.5 million tons per second that are being converted into energy. So, as I said, that's a really huge amount of mass it's losing each second. There is another answer that you could have given that no one did. Reinvents itself. I didn't talk about this, but the net result is 4 hydrogen atoms produces helium plus energy. And the energy is a little fuzzy there in what I wrote, but that's what's going on. So you could, I put an H instead of, what's the abbreviation for helium? HE. So that is what's going on in the center of our sun. So you could have said reinvents itself, and I would have said, well, that makes sense too, because it's converting hydrogen into helium, as the song says, where hydrogen is built into helium at a temperature of millions of degrees. Yo ho, it's hot. I said we wouldn't sing, I'm sorry. We'll do it later. All right, talking more about the inner planets. I think I've hit most of these things already. The inner planets have a high density solid rock. All of these have a high density solid rock. What other things do we know about Earth besides having a high density solid rock? What other things can you tell me about the geology of Earth? Because what we're going to do is we're going to say, do these other things have the same thing?
Water.
Has what?
It has a lot of water.
Okay, a lot of water. So do the other planets have water? Okay, they have found trace amounts of water on Mars, not the others. There's something special about Earth with water. The water, we believe, was not here when the Earth formed because it couldn't hold on to water. But when you get a big enough mass, it can hold on to water. And then if you have comets that come in and hit the Earth, those comets that are icy, the ice melts, bringing water. And so the Earth's water, we believe, came from comet impacts. Now, if the Earth got water from comet impacts, so should Mars, Venus, and Mercury. So why don't Mars, Venus, and Mercury have significant signs of water? Well, Mercury and Venus are really hot. Mercury's very close to the sun, doesn't have much mass, so Mercury really can't hold on to an atmosphere because of its low mass. Because that low mass is not holding on to an atmosphere, it would never be cold enough to hold on to water. Hence, any water that hits Mercury, it's going to be gone. Now, there probably is, I think there's evidence for, in regions of permanent shadow having some permanent ice on Mercury. It has to be permanent shadow. You had a question, Leslie?
Okay, no, I was just going to mention, so pretty much it's kind of like when it's like a really, really hot day, kind of like the drought that happened in California. That's the way to put it. Like when it gets like really, 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 really hot, and then it's like the water in a way. I don't know if that has to do with. I picture like water being there and then being overly hot and it just goes like it's.
Well,
you know,
if it's in the atmosphere, you don't lose it. But let's get to Venus because that plays into what you're talking about. Venus, it has a mass very similar to Earth's mass, and a size very similar to Earth. It's only something like 5% smaller than Earth. And so Venus, you'd think, should have virtually the same environment as Earth, except for one thing. It's closer to the sun. Because it's closer to the sun, it, of course, isn't going to cool quite as much as Earth. It's going to be a hotter climate. And because it's a hotter climate, on Mercury, it's never gotten cool enough for liquid water to form. And so any water that it had stayed in vapor, and that water that's in vapor then can be lost in the atmosphere if you don't have enough gravity. And so they believe that water on Venus is probably never liquefied. And so it has built this cloud cover of other gases that gives it a runaway greenhouse effect. And we talked about the greenhouse effect on Earth. It's necessary for life. Without the greenhouse effect, we're popsicles. But with too much greenhouse effect, we're Venus, which is a just super hot region that we couldn't live in. So the theory is, well, why do we not have a runaway greenhouse effect like Venus? Because it got cool enough for liquid water to form. Liquid water forming, not only does it stabilize the water in some ways, it also absorbs carbon dioxide out of the atmosphere, depositing it as rock. So we have lots and lots of limestone, which very well probably was carbon dioxide in the atmosphere at one time. But it's been taken out of the atmosphere and deposited as rock. So it's not participating in the greenhouse effect, giving us a much lower greenhouse effect. So water is one of the things about Earth that we're going to use to compare. We call it comparative planetology. Another thing, on Earth we have tectonic plates. We have these plates that slide around against each other. Is that happening on these other planets? The answer is no. Mercury has some things that are called lobate scarps, where they have signs that there has been collapse. They believe that's because of cooling, things shrinking when they cool. Mars has signs that it used to have, possibly some plate tectonics, but does not have any now. It has a very hard crust. In fact, Olympus Mons is the tallest mountain in the solar system. It's on Mars, and it doesn't cause Mars to sink. Remember, we talked about isostasy and that the Earth, where you have the continental masses, it sinks lower just like an iceberg, has most of it underwater. Well, mountains do the same thing on Earth. And so the tallest mountain on Earth, was it Mauna Kea? I get Mauna Kea and Mauna Loa confused every single year. But the tallest mountain on Earth is one of those Hawaiian islands, tallest going from base to the top. It's so heavy that it has sunk down significantly, so there's a moat in the ocean floor around the island because of the sinking. Whereas Olympus Mons has no sinking, very hard crust. Okay, we're out of time for today, so we'll continue with astronomy on Wednesday. Have a swell Monday.